And actually, yes, I wanted to start the presentation with like a kind of a personal note because like this is me in like 17 years ago. Nobody can recognize me, not even my mom. I really asked her, yeah, who is he? And this was PyCon Uno, like first edition of PyCon Italy, 2007 in Florence. Like Python was kind of very strange language in Italy. Like I think we were like 98 people or something like that. And this was actually my first public talk. And so, like this conference is kind of home for me, and it's very important. So being on this stage now, it's like, yeah, I'm nervous, excited at the same time. And but speaking of all the time that passed since that day, I mean, a lot of stuff happened. But I mean, I became friends with a lot of people at a conference. A lot of, I mean, this is actually from the last 2 years because I didn't find the old ones. And a lot of them are in the organizers. And I think that we should all say thank you to them. Yes. Because they do an incredible job for all these years. And well, I think that they never get enough credit, so yes, I wanted to do this. And like career advice for beginners, how do you get here? Well, you go to PyCon, you make a lot of friends, you drink barrels of beer, and then you hope that they invite you to here, yeah. And to be precise, when I say barrels of beer, I literally mean barrels of beer. Like this was like we were in Berlin 2 years ago. We were celebrating my new job at Anaconda, and yeah, that's a very nice moment that we all remember. And speaking of Anaconda, let's go back here. This presentation is hosted on pyscript.com, which is one project which I've been working on in the last 2 years. Now I switched. And super incredible, cool project to host browser-based Python apps, which runs in the browser. Very easy for like beginners, but worked very well also for presentation. So I think that time to start with the real presentation. The motivation for giving this talk is that I've been working on this topic for a lot of years. A lot of my career has been on PyPy. PyPy, the JIT compiler, not PyPI, the package index. PyPy is an alternative implementation of Python, which is famous for the JIT compiler, so it's something to make Python fast. And during my work on this project and related projects, I kind of got some understanding of some reason why Python is slow. But also, talking to people, I realized that some things that for me are obvious because I work on them like on a daily basis. They are not obvious at all for many people, and yet there are a lot of misconception and kind of not good understanding of why some performance characteristics of Python are like that. So I thought it was a good idea to like share my knowledge and hopefully find something interesting here. And so okay, I mean, like raise the hand. Who of you use Python? Okay, don't even, yeah, all of you, yes. But who thinks that Python is slow? Okay, who thinks that Python is fast enough? Okay, so why are we here? So the first myth that I often encounter by talking is exactly this one. Python is not slow, and it's fast enough. And it's kind of true for certain use cases. The sub-myth is that a lot of people say, well, Python is just a glue language, or nowadays the cool thing is, well, only the GPU matters. Like we want to do AI run on GPU. So if Python is slow, we don't care. Because all the important stuff run in the compiled code inside extension or GPU and etc. And like if Python is slow, we don't care. This is true. Again, for a certain set of programs, like this is like the set of programs that all the people that raised their hand before, like thinking that Python is fast enough, but they are in this category. But in my experience, as a freelance and consultant to help companies to make Python fast, well, there are a lot of programs which falls outside this category, and we'll see why, basically. So for this person, it's important to make Python fast or faster, but actually, we started 17 years ago with 98 people in the World Conference. Now we are like 800, and like we want to grow, and like the amount of all possible programs is much larger than the one that Python can be used nowadays. And it would be nice I mean, I love the language. It would be nice to be able to use it for more than just what we can. So I think that performance is an important aspect of this. And so yes, Python is not slow for the kind of program for which it's not slow, yes. But in general, we can do better. And like the broader topic of this is that, yes, even if for your particular use case, Python is not fast enough, well, you can just rewrite the part of programs which are slow in C or C++, so you make fast only the parts which matter. And this was actually true until a few years ago, but now, well, it seems that everybody uses Rust and not C++. But the same argument apply, actually. And what is the idea behind? And again, it's not false, but it's a bit misleading, I think. The core idea is that there is this principle, we call it Pareto principle. At this point, I was like tired already of writing slides, so I asked ChatGPT. Like, I'm here writing a talk about performance, and let's explain the 80-20 rule. And what is the 80-20 rule? I don't feel like reading ChatGPT. But basically, the idea is that very often you have 20% of the program being accountable for like 80% of the actual time spent running. Or it could be 90-10, but like it's a small part of the program is where you spend most of the time. So you can just optimize that small part and you get a lot of performance, which is true. Although then you quickly encounter this other principle, Hamdahl's law, and which basically says that when you are a system composed of two parts, if you optimize one a lot, well, then the other one becomes prevalent. And then it imposes like a kind of theoretical limit of how much you can get by making this part faster. And I think it's very easy to visualize it. So we start from a Python program. Let's use the mouse here. In which you have the inner function, which takes a lot of time, like 80% of the time in this visualization, and the rest of the program, like 20%. Then you rewrite it in Rust. And in this, like, we make it 10 times faster. And believe me, it's not easy to make it 10 times faster. And but then, like, the rest of the program is the bottleneck. It's no longer the Rust. And even if we make this function 10 times faster, the overall gain is like 3 times, something like this. And which is, okay, it's good. Yeah, we made your code 3 times faster, but if you need like a real 10 times speed up, well, you cannot with this strategy, basically. It's like theoretically impossible. And yeah, could be good for some use cases, but I mean, you see why you quickly enter into problems. And it's something that I actually saw in my career. Like, it's kind of easy, if you know how to optimize what's called the inner loop, which is the bottleneck, but sometimes, at some point, you no longer have obvious bottlenecks, and you don't know where to go with this strategy. And then we need to try to optimize the rest of the program. And then, well, a lot of people have this idea, like Python is slow because it's interpreted. So what does it mean exactly? Like, when you run a Python program, well, you run it using the Python interpreter, and actually what it does is to take your Python program, translates it into Python bytecode, and runs in the Python virtual machine. And this is what we call the interpreter. And it means that every single operation in line, like the A equals A plus B, well, every single operation is interpreted, but it's run by an interpreter, and then you get the result. So interpreters are famous for being slow because instead of translating to machine code directly your program, and so that machine code can like avoid this process of reevaluate the same code again and again, you have to redo the work at every line. I mean, very, very short explanation. And so you could just write a compiler instead of an interpreter. That's kind of the idea. And again, the sub myth of this one is, well, some big company in USA just announced yet another project which will use LLVM, so it will be fast, and then all the problem will be solved. I've seen this a lot of times, and most of the time they don't work. Why? Because the interpreter is only a very small part of the problem of Python. Imagine to take this very simple expression, like pi.x times 2. If you're writing in a low-level language, C, C++, Rust, you can compile this code to, well, do something very simple. You locate the address in memory of this expression, p.x. You load this in memory, you load the 2 in memory, you multiply, and you store the result in the target variable. But if you do it in Python, no matter if you are interpreter or compiler, there is a lot of logic that you need to implement if you want to comply with the semantics of the language. And a lot of logic is like this. I don't know how many of you are familiar with like the internals of Python, but it's like we need to look up p. To start with, where is p? Well, maybe it's a local variable, maybe it's a global variable. Well, we do it dynamically at every time. And an interpreter, a compiler, cannot help much. But then, yes, what is p.x? Well, C compiler can just know where in memory it is. But for Python, you need to find the type, call $getAttribute on the type, which could be a user-defined function, so you call other Python code, and then, well, time passes. And then you have pi.x, and then you want to multiply by 2. But then what does it mean? Depends on the type of x. So we get the type, we call this dundermul on the type. Wait, maybe we need to call ermul. Who knows the rule when you call dundermul and when you call dunderermul? Nobody? Okay, someone does. But I mean, all this stuff, and then we go, well, we continue, blah, blah, blah. All this stuff must be taken into account by any compiler. Like, if you want to implement Python language and not some kind of random subset which looks like Python but is not Python, you need to take this into account. And this is where you spend most of the time anyway. So if you just take a compiler and take Python and compile it to machine code, then the machine code does do all this stuff, well, it will be slow. And that's actually what happened multiple times. So yeah, this is not really the solution. So kind of the problem that I'm trying to say here is that when you want to do this operation, well, we don't know the types. So what can we do to improve? Well, nowadays, we have static types in Python. You can type functions and notate with types, so a compiler can have a much better and an easier job at producing good code. So in this kind of slides, I want you to think like a compiler. So imagine that you are a compiler, and you have this Python code, and you need to imagine which machine code to produce to be fast. But you don't know how this code will be used. I mean, there are various techniques for implementing compilers, but let's stick to the simple one. Like, you have a function, and you need to produce the code for this function. So I have this very simple function, takes 2 integers, returns an integer, x plus y. So we can do like C and Rust. Well, just load the values in memory, add it, return. And, well, this works. Print just works. So we can. But the problem is that, like, if instead of adding 2 and 3, I add hello and war, this is a perfectly valid Python program. It will work, because type annotation are actually ignored by the interpreter. And yes, we can use them as documentation. We can use tools like MyPy or PyWrite to get some kind of understanding and be more sure that our types are correct, whatever it means. But the interpreter or the compiler, well, cannot take for granted that the types that I declare are correct. It must take into account all the possible possibilities. else it's not Python again. And you could say, yeah, sure, you are kind of cheating because here, imagine that we are using MyPy, so I run a static type checker into on my code, and I could just say that it's mandatory. It's no longer optional, and I can compile code which must comply with the static type checker, and then the compiler has an easier job. So I could just say that, like this line, all the lines which are type ignore or similar, like no type check decorator or whatever, are forbidden and illegal. Then the compiler has a much easier job, right? Who thinks that I'm right? At this point, it should be obvious that there is something more. Like, this is still a perfectly valid Python code. I create a custom class with a $add method, and I have a function which takes to my class, objects, return one, perfectly works. And then somewhere later in the program, randomly, I delete the add method on the class. And yes, someone is doing like this very Italian thing. But yeah, well, we can debate whether it's good idea or bad, whether it's good code or not, but this is Python. This is the rule of Python. Complain with Guido, not me. If you are a compiler and you want to comply, you need to take this code into account. And it's not really theoretical. I mean, I don't know for this specific case, but when we're developing PyPy, we had to implement the full Python semantics because we wanted to use real Python code. We want to be able to import Django, import NumPy, all these big libraries, SQL Alchemy. And somewhere deep in this big code bases, there are crazy stuff. And in order to run them on an interpreter which is not CPython, you need to to be compatible with them. So if you want to run existing Python code, well, you need to take this kind of stuff into consideration. So static types, no. And so, okay. What I'm saying is that if you just want to take your Python program and do some kind of static analysis, like normal and classic compilers do, then you cannot do much because Python is too dynamic, too many corner cases. So what the other classic approach, like textbook approach, well, you can use a JIT compiler. And this actually works. Apart, it's the all. The all in all your problems in this sentence is the problematic part. JIT compiler actually work. PyPy is a JIT compiler and managed to make Python code very fast in certain cases. The CPython core development team is developing a new JIT compiler for CPython, which shares actually a lot of ideas in common with what PyPy explored. And the upcoming CPython JIT compiler will make some Python code fast. So it's actually a good thing. But then we quickly go into other problems, and these are very subtle, but I think that especially now that CPython is getting a JIT, they will become kind of prevalent in the Python world. One problem is that we have this kind of trade-off triangle. And you can have dynamicity of the language, you can have speed, and you can have a simple implementation. Well, pick two. You cannot have all of them. Like, in the last 30 years, CPython was on the left side. You had dynamicity, because the language is very dynamic, and you had a simple implementation. Simple with an asterisk, like CPython is a complex piece of code, but the implementation of the interpreter and the logic was kind of, well, textbook. You take your AST, you compile to bytecode, you have a virtual machine which interprets the bytecode. Everything was kind of easy to read. Like the C code of the CPython interpreter is very well written, very documented. Like if you are a student at the university studying this kind of topics, you can probably understand maybe not all of it, but some of it, and then if you spend more time, it's something doable. But if you want speed, then yes, you need a JIT compiler. For those who don't know, like a JIT compiler is a just-in-time compiler. It means that basically you run your program as with the interpreter, and then while you run the program, the interpreter collects information about what's happening. So for example, these two variables in this particular piece of code, they seem to be often integer or string, so I generate fast code for these cases. And then if something changes, like if some crazy guy deletes down the road on the class, then I can invalidate the code and generate it again. It's an incredibly complex piece of code, but it produces good results. So yeah, you can have a very complex implementation, keep your dynamicity, and get good speed. But then you quickly end up into what is the real problem of this approach, from my point of view, is that you lose predictable performance. With CPython, simple, like until 3.13 at least, it's very easy to predict the performance of a piece of code. Like, if you look at the bytecode produced, well, you kind of know that loadout takes, I don't know how many microseconds, and the store out some other. And I've seen colleagues in some companies doing exactly this kind of analysis, trying to optimize code by removing the bytecodes and knowing how much each bytecode costs. And this is very useful because you can see a diff of a pull request and kind of predicting or having kind of understanding, intuitive understanding of how the performance will look like. But if the implementation is no longer simple and starts to become complex, then you don't know, because the compiler does crazy stuff. And in order to understand how the performance looks like, you need to know very well what the JIT compiler does. And know that in this particular case, if these conditions are true, the optimizer can remove all the overhead and produce fast code. And if other conditions are not true, or this code is slightly different, then you don't know. And this is actually very good career advice. Because if you are one of the few people who understand how the optimizer works, well, then you get paid for doing this kind of stuff. That's what I did for 10 years. But like, in general, it's not super useful. I mean, it's useful. Like PyPy, as being useful, is still useful. You can use it for having fast code. But if you want to use it for super good performance, then it becomes hard. And then you arrive at the problem which I call optimization chasing. And it's, I kind of predict, maybe I kind of fear that, well, CPython will go down that route. Like, you start with a slow language, well, Python. And then you add optimization for what's called the fast path. Like, basically, the idea is, again, I have code, and I need to take into consideration all possible crazy stuff, but in practice, the crazy stuff doesn't happen. So I optimize for the fast path. And then I have something which is either same speed as before because the optimization don't kick in, or it's faster. So everybody's happy, job done. Yeah. Okay, I don't know what I wanted to say, but okay, sorry. What I wanted to say was good job, but yeah, whatever. But then what's happening is that time passes, and you start to rely on this kind of optimization, because you are writing code, and I write a library, I want it to be fast, I use all the kind of tricks which I know the optimizer will use for optimizing Python code, or simply, I have a program which works, and it can do this number of requests per second, or takes this number of seconds to complete, or whatever. And then time passes, and I'm sure that my code is still fast. Because what happens often is that I do an unrelated change somewhere, and then I get 2 times slowdown. And it's very, very hard to track it down. And again, well, I did it for a living for a while, but like it's like it quickly becomes impossible to do reliably. Like, you can optimize at a specific point in time, but you need to be an expert for it. And then you leave and you do something else, and then other people change the code, and then who knows what happens. I remember this time in which the code was suddenly very slow, and we didn't understand why. And then it was because it was still Python 2 times. We had a dictionary which contained only strings, and then at some point we put a Unicode string at a key in the dictionary, and then this was enough to kill one optimization, because you were no longer sure that all the keys were strings, and then you need to do a lot of checks, and everything was very slow. But I mean, this kind of stuff happen, and how do you track it down? Well, you need to look at assembly code, not easy. So, what is the actual problem that I'm trying to hint at? Like, we have all these possible solutions, and from my point of view, none of them work very well. What is the actual problem? Why Python is so hard to optimize? And I think that you can have a kind of understanding by looking at this code. I call it humans versus compiler. So if you look at this code, like you are reading the source code of some real world project, you know what is happening. Like, I'm importing NumPy, yes, sure, it's very obvious. I'm doing this calculation, I get arrays of floats, I get k, which is a float, I call this stuff, I call it .sum function, which is implemented in NumPy, I add 10, well, it's a constant, it's obvious. But from the compiler point of view, none of this it's possible to know because of what I showed before. A lot of things could change. For all I know, NumPy could be non-NumPy, because in Python you can hack the import system, and I could say that import NumPy, maybe it's something else, or not the NumPy that you think of. So, but this code never happened. In practice, this code is true. Like, it's using NumPy and for doing the sum of an array and multiply. It will never pass a code review if you do something completely crazy. So from my point of view, we have too much dynamicity. Like, dynamicity is what makes Python slow. So we could just remove it. Why do we have all this crazy stuff? I claim that it's also what makes Python awesome, because you can just use Java if you don't want dynamicity. But who likes to use Java? Okay, I have any Java? Yeah, okay, yeah. Sorry, sorry for the Java shaming. It's just an example. Like, it's totally. I mean, Java is a totally fine language for some use cases. I hope that to see some people saying this again. But like, the feeling of the language is very different. Python is dynamic, and the dynamicity of Python makes it possible to write awesome libraries. You can have SQL alchemy, which you write just your model as a class declaration, and then you get all this cool stuff with databases. You can write fast API, which generates a lot of code automatically for you. You can have NumPy. All this stuff are not possible in Java, so the dynamicity of Python actually is what makes it possible to write all the nice libraries that we like to use. So we need to, yes, find a balance. Speaking of dynamicity, this is a collection of, well, crazy stuff that can happen. You have very simple class point, two attributes x and y. I have a foo function which takes a point. I don't believe the type annotation because who knows type annotation? So I ask that that's the instance, and then I print the .name. So does it work or not? Maybe, because it's totally possible in Python to do something like this. You create a point and you add an attribute to the instance outside the init, and this actually works. Again, well, we need to take this into consideration when we implement the language. Is it a feature that we need? Maybe, maybe not. We can discuss. But you can do crazy stuff. This is a class that has a method 50% of the time, depending on randomness. So if I run this program, maybe it works, maybe it doesn't, I don't know. And believe me, this works. Like, it works in the sense that it does what I'm describing. Like, it's totally fine Python code, because inside a class statement, well, you can have statements, like you can have ifs, you can have functions, you can have for loops. Do we need it? Don't know. More crazy stuff. Other simple, very simple class. I have a student, it takes a name, and it has a method for studying. Yeah. But then I have a Berliner. Who lives in Berlin here? Few people. And then, well, Berlin people go partying. And note that the class Berliner is not even a subclass of student. It's completely unrelated. And then I create a person, and I I call a function, go to Berlin, and then I call study. What's happening here? What do you think it can happen? Well, I can do this. I can change the class of an object after the object has been created. And know that, I mean, the dot name is still there, but just the class is different. So when I call the study, then I call Berliner.study instead of person or student.study. And yeah, this is something that you need to take into consideration again. Makes Python slow. Another example. I have a class person, I have a class student, and here I'm instantiating a person. It takes a name and an age, and I print it, it works. And now I am sure that this is a person, come on. Like, I'm not calling anything else in between. What kind of trick can I do? I can do this. So in Python, you have the dunder init, which is what everybody uses, but you also have dunder new. And dunder new, you can do crazy stuff, including returning an object which is completely unrelated. Like in this case, I'm using it for saying that if the person is minus than 19, then I assume it's a student, and I just create another class instead of creating person, and then I assign a name. But I can really do unrelated stuff. I can return 42, and then it works. Like in the sense P is 32. And yeah. Other crazy example. I have two functions, foo and bar, both return n. N is 10. I check that are the same return value. I mean, an easy way to make this failing is to well, just like change the definition of foo. But yeah, you can do it. But what if I tell you that the foo has the exact same body? Like it still does return n, but this assertion is false. What's happening here? Well, it turns out that in Python you can take a function, take the code inside the function, and tell the interpreter to use a different dictionary for globals. What's happening in Python is when you do n, here return n in the expression, and it does a global lookup, so it checks what is the dictionary of the module, which is the globals of the function, and normally it's, well, the module, the namespace where the function was defined. But you can just tell Python to use a different one. So in this case, after I do this crazy stuff here, then bar returns 10 because it uses tscope, but foo returns 20 because I just telling it to use another scope. And again, you can say, yeah, sure, but who? Like, no, nobody does it. Come on, like this is, yes, it's cool, it's nice tricks. Turns out that this is real code on GitHub, and this is code from PDB++, which is a debugger for Python, and they do actually this kind of crazy stuff. So, does anybody use or know PDB++? Not many people. You should. Like, trust me, it's awesome, much better than the default PDB. Pip install PDB pp, and you will not regret it. It's basically hijack the import PDB mechanism, so you don't even have to change your imports, and you get color, syntax lighting, tab completion. And by the way, like, this is who wrote the code many years ago. And I claim that it was actually very good. I mean, I can explain it later if you want, but I think it was. It actually made the code better by using this trick. But then it makes my other life as a compiler expert, a Python implementer, much harder. So yeah, I need to balance myself. But from some point of view, all this dynamic stuff are useful because they let us to have to build abstractions, and actually it's what you do as a programmer. Like at the end, you have machine code, 0 and 1, and very low-level operation. And then with low-level languages, high-level languages, libraries, we build abstractions over abstractions to make complexity manageable, and it's good. it's good to have abstraction because it makes it possible to write more complex programs. But in Python, every layer of abstraction has overhead. I call this, I mean, there is a kind of abstraction which is like Python to Python overhead, in the sense that I start from example for a simple Python code. In this case, simple algorithm, I take a list of points, which is every point is a tuple of numbers, and then I do some computation, random function. I sum all of them, and I return res. Okay, there is a typo, but okay, it's not important. And but then, well, I want to put it into a function. So I put this code into a function. Turns out it is slower, because in Python, every time you call a function, well, you need to pay the penalty, speed penalty for, well, calling the function, passing the arguments, and etc. And then maybe I want to represent points as a class. This is like much nicer code from some point of view. But again, the fact that it's in a class and on a tuple, I need to pay penalty every time I do pay.x and pay.y. So this code is much nicer to write and to read than the first one, but every layer of abstraction in Python imposes a penalty. What a JIT compiler tries to do is to remove some of this overhead, but it cannot remove it completely. And it's kind of overhead that, for example, in C, you don't have. So, well, we are back. Well, let's rewrite things in C. But even in this case, an implementation, a JIT compiler, an interpreter, whatever, has a hard time to optimize stuff, because here you have your program, which is in two languages, part in Python, part in C. And every time you cross the border, well, you need to kind of invent a protocol for making the two languages to communicate. So if, for example, I am a JIT compiler, I recognize that it's a for loop of points, and I represent all my points nicely in memory. But then I call this function, which is in C. And the function expects, well, Python objects. So I have all my nicely optimized numbers in memory, and I need to create Python objects to pass them to the function, so the function can destroy the Python object to take the real numbers. It's this kind of overhead, like cross-language overhead, that is kind of impossible to eliminate fully. So yeah. The other problem, and this is a problem that nobody, really, literally nobody speaks about. Whenever I speak about Python performance, nobody speaks about this problem in Python. And I think it's very important, and I don't see a solution, is memory management. And in particular, we have a problem of, well, memory hierarchy. I don't know how many of you are familiar with like low-level details of CPU architectures, but in modern hardware, you have the RAM, you have the CPU, the RAM. The RAM is kind of slow, and you have level of cache to make these lookups faster. And some of your data is stored into cache L1, L2, L3. Every layer of cache is L1 is very small but very fast. L2 is a bit bigger and a bit slower. L3 is much bigger but a bit slow. And then you have RAM, which is gigabytes, but from this point of view, very slow. And then the CPU can predict which values you want next, and they try to put them in the cache. But every time this mechanism doesn't work, you have what's called a cache miss. You need to go back to memory, take the data, and it's very slow. And this is kind of animation which show you the relative speed of levels of cache. And like you see, if your data is in L1, well, it's super fast. It's kind of 2 CPU cycles. So like it's as fast as the CPU. But as long as you have cache misses and you go to RAM, well, you wait multiple hundreds of cycles. And basically, the CPU has to wait. Your CPU is not doing anything. Okay, lost the mouse. And Python is very bad at this. Because what the CPU does is to basically say, if I have data in this part of memory, then probably the next data is contiguous. It's close. And but in Python, if I have a simple list of persons, again, Alice and Bob, then what happens in memory is this kind of stuff. So the Python list is composed of 2 objects, and every object is a pointer to a person, and every field of the person is a pointer to a list, so it's to a string, or to a number. So if I want to do the average of all the ages, I need to follow a lot of pointers. This is called pointer chasing. Like you start from here and you go there, cache misses probably, because it's somewhere else in memory. And then I follow these pointers, cache miss again. And then I read the next item on the list, which was in cache before, but I trust the cache to follow the pointer. So I need to follow them again. This is like horribly slow. And there is basically no good solution for fixing it in Python. I fear that as the language as we know it is, well, just cache unfriendly, there is not much we can do, even with crazy JIT compilers and anything like this. So from some point of view, the sad truth is that at some point we can make Python super fast. That there is a limit that Python cannot cross, unless we want to break some of the existing compatibility that we have. And I would like, I mean, it would be nice now we have some kind of announcement to say, but no, like, this is like... Maybe. No, okay, I mean, it would be nice if I have this crazy announcement. Yes, I found a way to optimize Python. It's not true. But I feel that basically, as a community, as a language, like, if we want to move forward and make Python, like, I would like to avoid this, like, rewrite everything in Rust. Like, I would like to be able to write my thing in Python and be as fast as Rust. How can we move forward? I think that the only way is to, like, basically tweaking the language semantics. We can keep the dynamic parts which are actually useful, but maybe design the rules in such a way that are easy to compile, and like in such a way that we can remove the abstraction overhead, and we can have a type system which is oriented at performance, because the current type system of Python is kind of a hack on top of the existing language design, and it's not really designed for being useful for compilers to produce fast code. And we should somehow find a way to remove this C Python overhead, because if I want to use C libraries, I would like to be able to call from Python without paying the cost of the C API. But most importantly, we should find a way to stay Pythonic and have the feeling that we all know is Python. And yeah, I'm working actually on a project which I call SPY, which is stands for Static Python, but it's not. I mean, that's not the announcement. Like, it's not ready. It's with research, basically, work in progress. But basically, it's a language which kind of Python without the bad parts somehow, which try to fix all these problems and meet all the goals that I'm describing in this slide. I presented the SPY at PyCon 1 week ago. So if you follow this link, you can find the slides. And I think that in 1 month or 2 months, the video should be online. So it should be like, if you're interested, you can watch it. And while we're at it, another career advice, like, you know, like, documentation is super important. Do we agree, right? Yeah. Okay, I mean, sometimes I don't follow my advice because, like, this is documentation for SPY. Let's see, yeah, this is the README. How do I go back? No. Okay, so yeah, I think I'm done.
Thanks, Antonio. I think we have plenty of questions, and I think we have time for the Q&A session now. The first question, can I go ahead? Do you want to drink?
No, go ahead.
Wait. Okay. So, do you think a smaller standard library will make Python faster and more maintainable?
Removing the standard library?
A smaller.
No, I don't think so, because like the standard library, a part of it is just Python code, which could be just put somewhere else, but it doesn't make the life of the compiler any easier. Some of the standard library is written in C, but again, like, it's the same kind of C code that any C extension can write. So no, basically, it doesn't make any difference.
So the second question is breaking compatibility in the 3 versus 4 compatibility is, we did it once. I mean, I think it's
3 versus 4?
I think it's Python 3. Yeah, I think it's 2 versus 3 or.
Okay, can I read the question?
Yeah, because I don't know if the user is.
No. Okay. I think that this wants to say. Okay, we are breaking the compatibility, so we are going towards the Python 4.
Oh, okay, yeah.
So and then
3 versus 4.
Because for those who
okay.
are new in the community, 12 years ago or so, there was this 2 to 3 transition in which Python 3 broke the compatibility with Python 2, and it was a mess, and a lot of like problems in the community. It took forever. Nobody was happy, and that's something that the CPython code developers are very well aware. Guido, in particular, like he says very explicitly all the time that he doesn't want to do the same mistake again, and I agree. Like the problem of the 2 and 3, the 2 to 3 conversion was that you had to do it all at once. Like either your program runs on Python 2 or in Python 3, and you can't do any kind of incremental migration. What I have in plan for Spy is basically that you will be able to just write parts of your packages in Spy, for example, and still use normal Python for what you don't want to port. So, but what I'm doing is not Python 4 at all. It's a kind of external project.
Thank you.
You're welcome.
Okay, yeah, I just got an upvote on this question. So the first one now is another one. Any thoughts about Mojo language?
So it's not the first time that I hear this question, and I would like to understand, like, why do you ask about Mojo and not, well, Java or Go? I think that the counter answer to my question is usually because Mojo claims to be like a new Python, Python faster, and blah blah, and I say it's a lie. I mean, not a lie in the sense that they want to be bad people or anything like that, but Mojo is not Python. Like, it's something that has a Python compatible syntax somehow, but it's a completely different feeling. Like this what's happening here? This stay Pythonic is not true in Mojo. Like, Mojo is a language in which you need to take into account object ownership and things like this. Like, not Python. They claim to be that they will be compatible with Python eventually, but I don't see how, honestly. So yeah.
They said that it's a superset of Python.
It's not.
All right, so any tricks from other languages to make it more cache-friendly?
Yes. So it's not really from other languages, but there is a community in which, especially in the game industry, in which they use what is called like data-oriented design, and basically, to be cache-friendly, you design your data structure in a way that, like, you put the data close together in memory, knowing how you will use it. So for example, instead of having a list of persons in which you have a name and then the age, a name and the age, you can structure your data in memory differently, so you have all the names together and all the ages together. And then if you want to do the average, then all your ages are together in memory, so it's very cache-friendly and it's much faster. You can do these things in C++, you can do it in Rust. In Python, again, we don't have the tools. So this is actually something that I want to explore with Spy, having kind of tools for playing with this design.
All right. Next one is, how do you feel about compiling code from Python to C using Cython? That works for about 15–20% of programs.
Yes.
This
is okay. What's happening now? What did I do?
There you go.
Okay. So with Cython, we are in this. We have two problems. The first is this one. Even if you compile with Cython, then you still have to, if you take Python code without type annotation and compile with Cython, Cython has to do this stuff. So it removes a bit of overhead for the interpreter, but not the big of it. You can apply type annotations, but then you are in a strange, I've used it for a while to try to make a library super fast. And it's kind of hard because if you're just happy with some result, yes, kind of works. But then if you want to like have super fast, then you need to know exactly what Cython is doing, and then you change a line, you forget a variable annotation, the code still works, then it goes to the slow path, and so you are in another problem, which is this one, basically. And so yes, it works somehow, but I don't think it solves all the problem. And it's super cool piece of I mean, I don't want to sound too negative. Like all the project I'm talking about, CPython, JIT compiler, Cython, even Mojo, all super cool technologies, and thanks to all the people that work on it. Like I don't want to be like the one who wants to tell everybody how to write software. Like not at all. But each of these has limitations. Basically, that's what I'm saying.
Thank you. What about releasing the global interpreter lock?
This is a completely different topic, which I didn't cover, and it's very important because for those who don't know, Python has historically had a problem with multi-threaded applications because it has what is called it used to have what is called a global interpreter lock, which means that even if you have multiple threads in Python, only one of them can run at each time. And in the modern hardware, you have a lot of cores and CPUs, and you cannot use all of them with Python. There were workarounds, multiprocessing, release GIL in C extension, etc., but it was not good. Now, recently, the CPython developers merged a pull request to remove the global interpreter lock optionally, and now it means that we will be able to have free threading in Python for real and have full Python application. It's cool. It will make it possible to use multiple threads, but for every single thread, you still have the same problem that I'm describing. So the problem that I was describing in this talk are kind of single-threaded problems. And with multi-threaded, yes, you can use multiple cores, but you still have this kind of abstraction over rare and dynamicity. The other problem is that I predict a lot of seg faults. Like all the libraries, they were all the C extensions in Python. They were written knowing, or maybe taking into account, or maybe not even taking into account explicitly, but in practice they had a GIL, and it worked. And if you just suddenly remove it, well, they need to fix their code probably. So that's why it's experimental. You need to enable it at compile time. It's basically not stable at all. It's just a giant experiment that you are doing as a community. I think eventually it will work and will be a good tool to have, but I don't think it magically solves all the problems.
Okay, thank you. You show us a very exoteric feature from Python that dramatically slow down the language. Do we really need them? Why, in your opinion, they exist?
Okay, well, that's like a kind of philosophical question. Do we need them? Yes. Like some of them we don't need always, but there are cases in which we do. Okay, maybe deleting the attributes, the done add from the class, I never see it in real code. But adding attributes to the class dynamically, that's like methods to a class, that's something which I did. Changing the class of an object is something which I did. There are cases in which it's useful. But yeah, I mean, it's a trade-off. Again, I think that we should find a balance to keep the feature that we need and remove. And basically, it could be that this dynamic feature can happen very early in the program, and then we say, no, they are no longer allowed. So for example, meta classes are useful. With meta classes, you can have SQL alchemy, but they are very hard to optimize. But you can say that you can have meta classes when you import the module, and then after a while, they are no longer acceptable. Like they don't work. You cannot create new types at runtime. I think it's a very good balance because it gives you enough freedom to implement all the cool libraries that we want, but then it makes the life of the compiler easier. So this is one of the tweaks that I would like to try for making Python easier to compile, basically.
Thank you. I think we have time for another couple of questions because we started late, so we're going to recover that 5 minutes. So I think this is a funny one. So why you keep using type annotation in your code snippet in a presentation?
No real reason. Actually, I mean, well, when I wanted to show static types that don't work, but I needed them. And then it was like other documentation mostly, but yeah.
Okay. Okay. Next one is, what was the biggest mistake you found in a Python application as you debugging its performance? And what's the solution if you found one, and what we should definitely not do?
Oh, I'm not prepared to answer such a question. The biggest, I mean, some very strange stuff, I found them, and they were not actually mistakes, but for example, and that's a problem that PyPy had, and the new CPython JIT will have as well, is that existing programs are written with CPython in mind and with certain characteristics, and people, they're trying to optimize them for, like, you have a big project that has been going on for years, and you try to optimize it. You apply all the tricks to optimize for the Python that you have. And then you use new techniques, and then the performance characteristics are completely different, and something that earlier it was innocent, now it becomes extremely expensive. So a real case that was a big problem in PyPy was, I think it was Django. It was created, like you had a function, and then inside the function you create a class and return it. And they were doing it like every time you call the function. And in CPython, for the way it works, it's not really a big deal. But for PyPy, well, it assumed that the class is unique, and then every time you see a new one, then you have to throw away all the code. It was an incredible performance problem. What we did was to, well, put the class definition outside the function, and everything was fast. I mean, I don't think it was their fault, because when they wrote it, it was perfectly fine code, but stuff like this happened.
Thank you. Last question, and then maybe you can reach out to Antonio outside and asking for more questions. How does PyPy work with compiled extension modules?
Oh, it's basically another talk. Like I have 1 hour. PyPy works with C extensions by basically pretending to be CPython. The protocol to have Python and C to talk is what's called the C API, and it assumes a lot of stuff. It assumes that objects in memory are laid out in a certain precise way, which is the way CPython is using, and C extension knows how to deal with it. But for PyPy, we wanted to be faster. We had a garbage collector, different than CPython, and a lot of other stuff, so our layout in memory is different. So what we need to do is kind of emulate all the internal details of CPython so that we can, from the point of view of C extension, we look like CPython. But all of this is incredibly costly. There is a post by me, which I wrote on the PyPy blog 5-6 years ago, which actually goes into gory details of internals and why it is actually a problem, what we do to emulate reference counting and all the stuff, but everything is incredibly slow, but it works. And again, CPython will have the same problem when they will try to do more exotic stuff, I think.
Okay. Thank you, Antonio. Thank you again.